In this example, we're going to be investigating a linear transformation taking us from R3 into R3. We will define the transformation as the image of vector x1, x2, x3 will be x1 minus x2, x2 minus x3, and x3 minus x1. We're interested in finding both the kernel of t as well as the range of t. Now for the kernel of t, we are looking for the set of all vectors v such that the transformation of v is going to be equal to the 0 vector. So as such, we're going to be setting each of these, x1 minus x2, x2 minus x3, and x3 minus x1. We'll be setting this equal to the 0 vector. This allows us to set up a system of 3 equations with 3 variables. So x1 minus x2 is equal to 0, x2 minus x3 is equal to 0, and negative x1 plus x3, reversing the order for formatting in the matrix. Converting this into a matrix, our augmented matrix will be 1, negative 1, 0, augmented with a 0. Second row will be 0, 1, negative 1, augmented with a 0. And then negative 1, 0, 1, augmented with a 0. I'll be interested in taking this down to reduced row echelon form. And I'm feeling pretty confident that I can do this without a calculator. I believe that if I were to add the first row to the third row and then add the second row to the third row, we would wind up with a row of zeros. If I take negative 1 times the third row and make that the new first row, and then leave the second row as is, I believe this would be what our reduced row echelon form would look like. We can identify from this form that x1 is a lead variable, x2 is a lead variable, and x3 would be our free variable. So we'll let x3 be equal to t. This means that the kernel of the transformation, if we interpret the first 2 rows and solve appropriately, the kernel of t is going to be equal to the set of all vectors of the form. Well, let's see, this one says that x1 minus t is equal to 0. Second says x2 minus t is equal to 0. So x1 will be t, x2 will be t, and x3 will be t, where t is some real number. And indeed, if I do t minus t and t minus t and t minus t, I will get 0 for all of those. We can also point out that a basis of the kernel would be the set containing the vector 1, 1, 1. And as such, we can also identify the dimension of the kernel, which is known as the nullity of t, as being 1 for this one-dimensional vector space. Now, as far as a range is concerned, we're going to be setting up something very similar. I'll go ahead and flip over to the other side. For the range of t, this is where we are going to be finding all possible w such that w is an image of a vector v. So we're going to define w as being the vector w1, w2, w3. So what we would be saying here is that vector v1 minus v2, v2 minus v3, and v3 minus v1 is equal to the vector w1, w2, and w3. Which means, once again, we can set up a system of 3 equations with 3 variables. v2 minus v3, that's w2, and then negative v1 plus v3 is equal to w3. Please note that this is the same coefficient matrix as what we got for the kernel, and that coefficient matrix is known as the matrix of t. So 1, negative 1, 0, 0, 1, negative 1, and negative 1, 0, 1 for the coefficient matrix. These will represent the coefficients of v1, v2, and v3. For the augment, we'll include a column for w1, a column for w2, and a column for w3, which means that we are augmenting with the identity matrix. This is the same technique that we would use to figure out the span of a set of vectors, or more specifically in this case, this is the same as the column space of the given matrix. Now this time I think we're going to have a little bit more difficulty taking this to reduced row echelon form without the use of a calculator, so here we have a calculator. We're looking for a 3 by 6, and we're looking for this combination right up here. So 1, -1, 0, 1, 0, 0. 0, 1, -1, 0, 1, 0, and -1, 0, 1, 0, 0, 1. I did that entirely too fast, so let's just check to make sure that everything got inputted correctly. And it's looking pretty good. We'll go ahead and take this down to reduced row echelon form. Too many parentheses. All right, getting a favorable result. First row 1, 0, -1, 0, 0, -1. Then we have 0, 1, -1, 0, 1, 0. And there's the good stuff right there. Now, here's where we get to give a little interpretation, specifically in this third row. According to our column labels, this is telling us that W1 plus W2 plus W3 is equal to the 0 vector. So if we're interested in a range of t, the range of t is going to be the set of all vectors of the form W1, W2, W3, such that W1 plus W2 plus W3 is equal to 0. Now, if we're interested in a basis of the range, we can treat this the same as we treated the column space. We can identify that we have a lead 1 in the first column and a lead 1 in the second column, and go back to the original to get these two columns and treat those as our two basis vectors. So that would be 1, 0, -1 and -1, 1, 0. You'll note that both of these two vectors do obey the above relationship in the sense that 1 plus 0 plus -1 is 0, and -1 plus 1 plus 0 is 0. The dimension of the range, also known as the rank of t, would be equal to the number of vectors that are in that basis. Then, to verify the rank nullity theorem, the rank of t plus the nullity of t winds up being 3. And the significance of that 3 is that 3 is the same dimension as our codomain. Wait, codomain? Domain. Crap, they're both 3. I'm going to have to look it up in the book. Let's see. Number of columns. And the reason that we had 3 columns is because we had 3 variables. Domain! It's the domain. Yes. Yes. I am more sure of it now. Hooray!